Alright, hello everybody, welcome back to Math 352. So this is the first one of our actual lectures that I'm going to be posting on YouTube for this course. And so just before I get started on it, just a couple of quick notes about how you might use these lectures. So I suggest you don't necessarily just watch the video straight through. Hopefully you've got either a copy of the PDF notes beside you, or if you haven't got that you can take notes on paper yourself, that doesn't matter. But I suggest you keep your finger near the pause button, so if I'm going too fast or you're not getting something, you can just pause it and watch it again. If you work your way through this lecture and can follow all of it, then you'll be doing really well. Okay, so also if anything comes up that you don't quite understand, just take note of it and bring it up at the help sessions that we'll be having starting from next week, starting from the week of the 21st. Okay, so it seems like an age ago that we had our first lecture, but we've finally made it to lecture 2. Okay, so if you remember, the first lecture was about matrix multiplication, and we're jumping towards another kind of fundamental linear algebra topic next, and that's the topic of orthogonality. Okay, so you've probably come across orthogonal things before. You've probably got a notion in your heads of things being at right angles, or things being perpendicular. You might be thinking of orthogonal transformations like rotations and reflections. Okay, we'll cover off these things during this lecture, and just kind of tie together some of the threads that you'll need to know to understand some of the work that we'll be doing a bit later. Okay, so moving on to our first slide. Okay, fundamental to the notion of orthogonality is the inner product. You may know this is the dot product. If we've got two vectors, basically the inner product, written x star y or x transpose y if they're real, is just the sum of their components. Okay, so if I had a vector, for example, x equals 1, 2, 3, and y equals -1, 2, 8, then our inner product, x star y, is just equal to 1 times -1, plus 2 times 2, plus 3 times 8, and if you're any good at adding, which I'm not always, that will be 24 plus 4 is 28 minus 1, that's 27. Okay, so that's our general vector product that we usually use. Okay, Euclidean length can be expressed as an inner product. Well, you know that by Pythagoras. If you've got a triangle with two sides like this, these can be the two components of a vector. Let's say that one is 2 and that one is 1. Then what we've got in here is the square root of 1 squared plus 2 squared, or if you think about it, that's 1, 2 times 2, 1, and a square root of all that. Okay, so the Euclidean length can be expressed in this form, which is useful to bear in mind when we're proving things. And this symbol here, which you may or may not have seen before, that denotes the length of a vector. Now I'm just using it in this lecture as Euclidean length, but the concept is a bit more general than that, and we'll get into that more next lecture. Okay, finally, you can use an inner product to define the angle between two vectors. Okay, and that's just the usual angle formula that you will have seen before. Now in particular, if the angle between two real vectors is 90 degrees, okay, then their cosine is going to be 0, and in that case we'll say that the two vectors are orthogonal. Okay, right, so dealing with orthogonality, unfortunately this word gets used a little bit differently in a number of different contexts. Basically we can have vectors being orthogonal, we can have sets being orthogonal to each other or to themselves, we can have orthonormal things, and yeah, so let's just quickly check to see what we mean by each one of these. So two vectors x and y are orthogonal if their inner product x star y is equal to 0. Okay, that we all know that one, so that's fine. Okay, we can easily generalize this to two sets, big X and big Y. We say they are orthogonal if you take one vector from one set and take one vector from another set, and they are orthogonal. Okay, their inner product is 0. And if that's true for every possible pair you can choose, then the sets themselves are orthogonal. Okay, a single set is orthogonal if you draw two vectors out of it and take their inner product, and they are orthogonal, no matter which two you choose. Okay. Also, very relevant and very important are orthonormal sets. Okay, they're just an orthogonal set where every vector has been scaled to have length of 1. Okay, and finally a quick statement. Vectors in an orthogonal set are linearly independent. Now I'm wondering if you remember how to prove that a set of vectors is linearly independent or not, but I can't ask you because you're not there, so I'll show you. Okay, so remember that if we've got vectors x1 through to xm, okay, so here's our set, and they're orthogonal, so any inner product of two vectors there is 0, then what we have to prove that a1x1 plus a2x2 plus am xm equals 0 if and only if a1 through to am equals 0. Okay, in other words, if you rearrange that formula, that says that no vector can be written as a linear combination of any other ones. Okay, and how would we prove that? Well, it's actually quite simple. We just take the inner product of this whole expression with one of the vectors and see what happens. So, what do? Well, we can take, I'll pull out xi, so just a general one. Xi transpose a1 x1 plus ai xi plus am xm. Okay, if our first statement is true, then that one's true as well. Okay, and we can expand this out, so we get a1 xi transpose x1 plus ai xi transpose xi. Okay, I'm working with real vectors here. I could be using a star instead, but I'll just mix that up a bit. Plus am xm transpose xm. Sorry, xi transpose xm equals 0. Okay, it's just expanding that expression. Now we know that our set is orthogonal, so this here is 0, this here is 0. In fact, all of these terms are 0, apart from this one, and that one there is just the norm of xi squared, or the Euclidean length squared. Okay, so this means that ai times the length of xi squared equals 0. And finally, what does that tell us? Well, because x is not 0, because it couldn't be in the linearly independent set, this means that ai must be 0, okay? Okay, so to complete the proof, you just repeat that same process for all the vectors, x1 through to xm, and that would show that all of the a's are 0, and therefore the set is linearly independent. Okay, so that's just covering briefly what orthogonality means when we're talking about vectors. What can we do with these that's useful? Okay, well, inner products can be used to decompose arbitrary vectors into orthogonal components. What does that mean? Okay, so to make this a little bit more concrete, if we've got two vectors q1 and q2 who are orthonormal, remember that that means that they're orthogonal to each other and length of q1 and the length of q2 are both equal to 1. Okay, and we've got some other vector v which is completely arbitrary. Then, using this formula that I've written down here, we can produce this other vector r which is orthogonal to q1 and q2. Okay, how do we demonstrate that's true? Well, we just test it. Okay, so q1, I'll use complex notation this time, q1 star r is equal to q1 star v minus, okay, q1 star v is just a constant, so I can just leave it as it is and take the q1 through to here. Okay, and minus q2 star v q1 star q2. Okay, great. So that equals q1 star v minus q1 star v times, well, remember that q1 and q2 are orthonormal, which means their length is 1. q1 star q1 is just the length of q1 squared, so that's just a 1, minus q2 star v times, well, the two are orthonormal, so therefore their inner product is 0. That just leaves us with q1 star v minus q1 star v, which is equal to 0. Okay, the same thing holds for q2. Okay, so this vector r is orthogonal to q1 and q2. So if we rearrange this formula, we have that our vector v, which is our arbitrary vector, is equal to r plus q1 star v q1 plus q2 star v q2. So what have we done here? Well, basically we've taken our arbitrary vector and we've split it up into 3 components, each of which is orthogonal to each other. Okay, so we know that q1 and q2 are orthogonal. Scaling them by a number is not going to change that, and we've just proven that r is orthogonal to both of them, so we've split our vector v up into 3 orthogonal components. Alright, so this one is actually, it'd be nice to just do this in MATLAB quickly, just to get a bit of a feel for what we've actually done here. So what I've set up, I've got 2 vectors here in MATLAB, q1 and q2, which are hopefully orthonormal. Okay, so I've run that. Let's just see what they look like. q1, there it goes, q2. Okay, to check that they're orthonormal, we should just take their inner product. Okay, the inner product is equal to 0, and we should check that their lengths are both 1. So norm of q1 is equal to 1, and the norm of q2 is also equal to 1. Okay, that's great. Okay, so we've got our 2 q1 and q2 orthonormal vectors to start with. Okay, the next part was to generate an arbitrary vector v, so I'm just going to make a random one. There it goes. So here's our random vector v. In fact, let's make it bigger, just for fun. And I'll make them normally distributed random numbers instead. Okay, so we get some negative numbers too. Okay, so here's our v. Now what we were doing is we're going to say that r, using the expression we just looked at before, we're computing this component r, which should be orthogonal to q1 and q2. Okay, just using the formula just from before. So why don't we check to see whether r is orthogonal to q1. So q1 star, or transpose in MATLAB, times r is equal to, well, as near as you can get to 0 on a computer, apart from being 0 basically, and q2 also very close to 0. Okay, just a note, if you're not very familiar with working with floating point numbers or numbers on a computer, in MATLAB, in its default settings, any number near 10 to the negative 16 is effectively 0 to near rounding error. Okay, so if you're seeing the result of a computation being something around about 10 to the negative 16, that means you've basically got 0. Okay, so I'm saying that I have 3 orthogonal components here, which should make up my vector v. So why don't I take r? That's r. R plus q1 transpose v times q1. Okay, there's 2 components there. Add on the last one. q2 transpose times v times q2. Okay, we've just checked that those 3 things are all orthogonal, and that should be equal to the vector v we had before. Okay, and if we take away v, for example, at the end, we get something very close to 0. Okay, so that just demonstrates what we just did on the lecture before. So we can use these ideas to split vectors up. Given some orthonormal ones to start with, we can find components of vectors which are orthogonal to what's already there. Okay, so moving on, we can generalize this idea. If you have an orthonormal basis for, in this case, Cm, that means we've got vectors q1 through to qm who are orthonormal, and they form a basis for Cm. That means you can make any vector in Cm out of them. Then, using the same ideas we just used, v is completely decomposed into m orthogonal components in the directions of the qi by an expression just like what we worked with before. Okay, now you've noticed that rather than just writing it how we did before, okay, so this is the type of expression we had on the previous slide, we've written this in a separate way here as well, which is a bit different. Okay, so what does this one here mean? This says that v is equal to the sum of, actually, I should probably change colours, scalar times qi. Okay, and we work out the scalar by taking the inner product of qi with our vector v. Okay, and we multiply that by qi. But we can write this in equivalently as qi star times v. Well, how do we do that? Well, basically, this expression, this term here, is just a constant. So we pull it out to the outside. So we've got q1 star v, q1. Because this here is a constant, we can move it to the other side of q1. Okay, and because matrix multiplication is associative, we can write that as q1 star, we can do that multiplication first, times v. Okay, so just quickly think, q1 is a column vector, so q1 star is a row vector. This here is a m by m square matrix. Square matrix. Okay, a couple of other things about it. It's rank 1. Okay, if we were to generate one of these, you'd notice that every row was a multiple of every other row. Okay, in fact, let's just do one. Oh no, let's not. Okay, so that's a rank 1 square matrix, and that gives us the component of V in the direction of Q1. Okay, so that's really neat. So we've got a matrix now that when we multiply by V, it gives us the component of V in the direction of one of our vectors. Okay, so this type of matrix is called an orthogonal projection. Okay, so we're going to cover these more a bit later on, but this is our first time we've met them. So this is a sum of orthogonal projection. So we haven't actually defined that properly yet, but we'll get to that later on in the course, times V. Okay, so it's a sum of some operation on the vector which gives us all these different components in the direction of each of the QIs. Okay, so you've probably seen these ideas before when you've studied the Gram-Schmidt process in stage 2, but we're just sort of tying some of these ideas together here. So moving along. Okay, unitary or orthogonal matrices. You've probably seen orthogonal matrices before. You may or may not have seen unitary ones. Basically, a unitary matrix is just the complex version of an orthogonal one. And we define them just like what we've got here. So a complex matrix is unitary if its adjoint is equal to its inverse. Okay? Or in other words, Q star Q is equal to I. Now if we're dealing with real matrices, which we very often are, in fact almost always are, in this course anyway, a real matrix Q is orthogonal, which is exactly the same thing, if Q transpose is equal to Q inverse, okay, i.e. Q transpose Q equals I. So that's our definition of an orthogonal matrix. Okay, so just like we were doing last lecture, we can write down our orthogonal matrix in terms of this expression here, in terms of the columns of Q. So we've got ourselves a matrix Q, has columns Q1 through to Qm. Okay, so this here is Q. This here is Q star. Okay, so when we take the adjoint or the transpose of a matrix, we can just write the columns as transposes themselves, and we get an expression that looks like that. Okay, and we know that if our matrix is unitary, then on the right we've got our identity. Okay, so just think for a second, what does this expression here tell us about the sets of vectors Q1 through to Qm? Well, what we're going to do is we're going to look at this matrix expression there, and we'll look at a single term of it. Okay, so for example, if we want to find the I don't know, let's say the 2, 3 entry of Q star Q. We can tell that we'll get that by taking the second row inner product with the third column. Yep, and if we were to look up in our identity, that's not on the main diagonal. Row 2, column 3 is here. So that equals 0. Okay, so you can see that that's actually true for any pair of vectors you take where I and j, so qi and qj, where I and j are different. Okay, so we can generalize and say that qi star qj equals 0 for I is not equal to j. Okay, well, what about if I is equal to j? Well, then we'd have, for example, q2 star times q2. That just is equal to 1. Okay, so if I is equal to j, then that inner product gives us a 1. So a matrix Q, if it's orthogonal or unitary, has an orthonormal set of columns. Okay, each vector is orthogonal to each other and has a length of 1. Therefore, the columns of Q form an orthonormal set. Okay, does that make sense? So we've got m of these vectors, and if the matrix is orthogonal, then they're an orthonormal set. Okay, and in fact they're an orthonormal basis for Cm. Okay, moving along. Okay, so remember last time we had a lecture, which seems like an age ago, we were talking about matrix multiplication. Okay, so cast your mind back for a moment. This expression here, what does that mean? Okay, so unfortunately we didn't do it yesterday, so it's not quite as fresh in our minds. But we were talking quite at length about the interpretation of this expression in a way that's not necessarily the same as you've done it before. So just to recap, this expression can be written in terms of the columns of Q. So Q1, Q2, Qm, x. In fact, I'll write the vector x out in full as well. x1, x2, through to xm equals b. Okay, so that means that b equals x1 q1 plus x2 q2 plus xm qm. Okay, a linear combination of the columns of Q. Okay, so this is the interpretation we talked about last lecture. When you multiply a matrix by a vector on the right like that, then you can think of it two ways. You can either think of the matrix doing some kind of transformation on the vector x to give us that vector b, or you can think of the vector operating on the matrix by taking a linear combination of its columns. Okay, so think of this as, well, the point B, that might be some kind of point in space. Okay, so B is our point. What this is saying is that if we take the basis consisting of the columns of Q, then we can construct B as a linear combination of those basis vectors Q1 through to Qm. Okay, so the vector x is like a vector of different coordinates for that same point when we're talking about the basis Q. Okay, so let's just write that one down. Therefore, as B can be written as a linear combination of the columns of Q with coefficients x x are the coordinates of B relative to the basis Q1 through to Qm. So what we're really doing, if we can figure out what x is, then what we're effectively doing is we are changing basis. Okay, so if we can find x, we are changing basis from E1 through to Em to Q1 through to Qm. Okay, so let's just add in an extra page here, new page after. So if we can find x, we are changing basis from E1 through to Em to Q1 through to Qm. Okay, now for an orthogonal matrix or a unitary matrix, it's actually really easy to do this. Okay, so we've got Qx equals B. Conceptually, we know that x therefore equals Q inverse B, and for a unitary matrix by definition, that's equal to Q star times B. Okay, so we can find x just by multiplying by the adjoint or the transpose of that matrix Q. Alright, well that sounds a wee bit airy-fairy perhaps, so why don't we just do a concrete example in MATLAB again, just so we can see how this works in practice. Okay, so let's just clear away the junk we had from before. Bye-bye. In fact, I'll just make sure my space is empty. So what I'm going to do is I'm going to bring up a little picture, hopefully. Yep, there it goes. Let's just bring you out there. Come back. Okay, so what I've got here is I've got my axes in black, and I've got a square. Okay, so think of the square as just 4 points. I've got 4 points at the 4 corners of the square, here, 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 and here. And what I want to do, potentially, is to express those points in a basis that corresponding to a different set of axes. Okay, so let's just draw those new axes on here. So here's a new set of orthogonal directions, and if I've got, say, a new x1 direction or new x direction along here, and a new y direction along here, I might want to know what are the coordinates of my square in that basis. Okay, so you might take a guess. You might say, alright, well if this is my new x-axis, then the 0, 0 is going to stay the same. This point here, which did have coordinates 1, 0, is now going to have coordinates, well, the x value will be a bit less than 1 probably, maybe 0.9 something, and the y value will be maybe negative 0.2 or 3 or something like that. Okay, so you can see that if these were our axes, just by eye we could sort of see what the new coordinates might be. That would be 1 point something, maybe 0.7, I don't know, and you can see that we get the different coordinates at this point here too. So the mathematical problem we want to do here is, can we find out the coordinates of that square in our new directions? Okay, well why don't we'll first define what those new directions are. Okay, so if you remember from the slide we just had before, the columns of that matrix Q were the basis that we wanted to express things in. Okay, so that they will be the two directions that we're interested in. So first I'll define this one. So Q1 is along this direction here. So Q1 is the vector, see, x goes across by 2 and y goes up by 0.5. Okay, and we're always working with column vectors. Now the basis has to be orthonormal, so I'm actually going to normalize that as well. So Q1 is equal to Q1 divided by its length. There we go. bit uglier, but it works. Likewise, Q2, well, if we're looking at Q2 in this direction here, then the x is negative 0.5 and the y is up by 2, and we should normalize our Q2 as well. Okay, I'm just going to move this up a little bit so you can see a wee bit more. Okay, so those are our vectors. So let's just check that they're orthogonal. I haven't done something wrong. Q1 transpose times Q2 is equal to 0. Great. Length of Q1 is 1. Length of Q2 is 1. Okay, so we've got our two directions there. Now, we can stick them into our matrix Q, just like that. And what we said just before was we can get those coordinates x in this new basis by multiplying by Q star. Okay, so if I were to flick back to my previous page, I can figure out x by just computing x equals Q star times b. Okay, so flicking back to MATLAB. Now I'm just going to wait for a second because I know these videos sometimes have a bit of trouble with me transitioning between writing and MATLAB, so I'm just going to give it a moment. So hopefully the picture's up by now. Okay, so we should be able to work out x as Q transpose times b. Okay, we should actually tell you what b is first. So b, I've got 4 different b's I'm interested in, now the 4 corners of my square. Okay, so those are my 4 points. So in fact, let's just plot them. Plot the first row versus the second row, and let's plot them as red dots. There they go. Okay, so there are my 4 b's. So if I want to work out Q transpose times the first one, okay, that just means all rows, first column of my set of points. Lo and behold, 0, 0 remains as 0, 0 in our new axes, our new coordinates. Okay, let's have a look at what happens to the point 1, 0. Okay, so it's the second column of my points matrix. So Q transpose times that b, we reckon, just looking at that point there, that it should be x being slightly less than 1 and y being slightly negative. Okay, you can see that there. There we go. X is equal to 0.97 and y is equal to negative 0.24. Okay, looks pretty good. Now we can actually do the whole lot at once, just by multiplying our points matrix by Q transpose. Okay, because when you're multiplying a set of columns by that matrix, you can just take the matrix inside and multiply each column individually. Okay, and that there are the coordinates of our new points. Okay, so we can just finally maybe plot this thing with our new axes just going straight. So if we were to do that, let's just plot the axes again. Clear our figure, bye-bye. Plot our new axes. There they go. And we'll do our make it looks better bit. I better call out something. Points 2 equals Q transpose times points. And I'm going to change this command to being point 2, points 2. And there you go. So relative to our new basis, that's what the square looks like. It's just what we thought it would. Okay, so you can see, the other interesting thing that we can see here is that multiplying by our orthogonal matrix basically just rotated that square. Now that wasn't an accident, that's always true. Well, to a point anyway. It's always true that if you multiply a vector by an orthogonal matrix, or a unitary matrix, then what you'll get is a rotation, or possibly a reflection as well, of what you saw. Okay, the key thing here is that none of these lengths change. Okay, it still looks like a square. The sides still have the same length. The angles between two vectors in this square are still the same. Okay, so we've preserved these Euclidean properties like length and angle when we multiply it by our orthogonal matrix. Now it turns out that this is always true. Okay, you're always going to preserve these properties when you multiply by an orthogonal matrix. And that turns out to be a really, really handy property that we're going to utilize quite a lot in the next few weeks when we're doing some of our matrix decompositions. Okay, so let's just skip back to our slides and move on to the next one. Okay, so just as I was just saying, when we multiply by a unitary matrix or an orthogonal matrix, hopefully by now you're getting used to me using these terms kind of interchangeably, lengths are preserved and angles are preserved. Okay, like I said before, you can work out the angle between two vectors by computing their inner product. So this statement I've got here is equivalent to saying that the angles are preserved. Okay, these are actually quite easy things to prove. So prove that norm Qx is equal to the norm x. Okay, how do you do that? Well, the norm of Qx squared, or the length squared, we know that's equal to Qx star times Qx. Okay, that's what we said before. When we take the adjoint of a product, it's the same as the product of the adjoints, but with the vectors and matrices written in the opposite order. So x star q star times qx equals x star q x, and because q is unitary, that matrix product there is just the identity x star ix equals x star x, which is equal to the norm of x squared. Okay, and because lengths are always positive, this is also true. It's also true that norm of qx is equal to the norm of x. Okay, so that's quite straightforward. Alright, well how about angles? How can we, well basically we deal with that in almost exactly the same way. So angles are preserved. Let's get another page again to do that one. Prove that qx star qy is equal to x star y. Okay, this is really easy. It's the exact same thing we just did before. So qx star qy is equal to x star q star q y equals x star iy, just like before, equals x star y. Okay, so that's really nice. So when we're multiplying by a unitary matrix or an orthogonal matrix, the key thing to remember, or one of the key things to remember, is that we're keeping the length and the angles between two vectors constant. So we're just rotating and reflecting them if you're thinking of it geometrically. Okay, well that's the end of the first lecture, I'm pretty sure. Let's check the normal slides. Yep, so I've gone a little bit under time, so that's actually quite good. So I guess you'll get this soon enough, and I'll be seeing you sometime soon. So just remember to keep an eye on the course webpage and your email inboxes for any news, and do let me know if you've got any questions. I'm more than happy to answer emails pretty much any time at the moment. So it'll be great to see you soon. Alright, see you later.